everyone. Thank you for coming. So I'm David. I'm at Stanford, and this is joint work with the A/B testing platform Optimizely. I'm going to be talking about... Is that better? Oh, that's much better. Thank you. OK, so I'm going to be talking about a problem that is pretty pervasive in A/B testing, which is peeking at your experiments. And I'm going to be talking about a solution we deployed at Optimizely at the beginning of 2015 that we call Optimizely Stats Engine that was designed to solve this issue. OK, so first of all, I'm just going to tell you a bit about Optimizely and what an experiment in Optimizely looks like. OK, so a typical Optimizely customer is an e-commerce site. And they will test out different versions of their website. So a canonical example is maybe they want to move from a gray checkout button to a red checkout button. Optimizely will host the experiment, so they will randomize traffic to 50% see gray, 50% see red. And then Optimizely will track lots of interesting metrics, such as what proportion click on the button in each group. And then Optimizely will communicate the results of the experiment to their customers on their results page. They'll output a bunch of stats there. OK, so experiments in Optimizely fall into two general categories. So the first are binary metrics. So that's this example of the click-through rate on a button. In each group, you measure a binary response on each person. So do they click on it or do they not? And we say that in group A, they click with some probability mu A. And in group B, they click with some probability mu B. So now the question of quality here means, is mu B any bigger than mu A? OK, so that's type 1. And then type 2, Optimizely tracks various metrics which takes continuous values. So an example would be how long the customer spends on the website, if you're trying to drive engagement, or if you're like e-commerce, then how many dollars does the customer spend? Now there's like a bunch of models you could use for these kind of metrics. For the sake of this talk and for the paper, we could look at normal models. So we say that any visitor comes in and spends a normally distributed amount of dollars, and we say the mean of that distribution is mu A if they were assigned to group A, and mu B if they're assigned to group B. And now quality here means which treatment gives you the higher mean. So is mu B any bigger than mu A? And yeah, so we assume that the two groups have common variance sigma squared. For the sake of this talk, I'm going to treat sigma squared as known, although in practice it's not, and in the paper we have some stuff to do about estimating sigma squared. OK, so either way, binary or continuous, the goal is to measure this improvement mu B minus mu A. OK, so this is what the results page in Optimizely looks like. They communicate the results through p-values and confidence intervals. So on this graph, this is 1 minus the p-value. Back in 2015, they called that quantity chance to beat baseline. And whenever, at any stage during the experiment, when n visitors have arrived, Optimizely will compute the chance to beat baseline based on the data available so far. And this is a p-value for testing the null that there's no difference between A and B. So mu B equals mu A, theta equals naught. OK. So what is a customer of Optimizely meant to do with that information? Well, they're meant to set a fixed sample size in advance. So they say, I'm going to wait for n visitors in A and n visitors in B. At that time, I'm going to read off these metrics. So they're going to read off the p-value and the confidence interval. And now, if the p-value falls below some threshold alpha, say 5%, they're allowed to reject the null hypothesis of there being no difference, and they can say there's a statistically significant difference between variation A and variation B. OK, now the purpose of this is that this frequentist test controls the type 1 error rate. So if there really is no difference between A and B, there is no, the risk is no greater than alpha. There's no more than alpha probability that you'll falsely reject the null. And now this frequentist test is tailored to give you as much power as possible. So once the customer has picked their alpha and they've picked their sample size n, this test detects any true differences with maximum probability. Now, okay, so for fixed n, it detects any effect with maximum probability, but small effects will have a low power, low chance of getting detected, whereas high effects will have a high chance of getting detected. So they've got to pick they've got to think about the typical magnitude of an effect they're going for, and they've got to pick their n accordingly when they set up their experiment. And Optimizely provided various tools to help them do that. Okay, so that's all well and good. So what went wrong? Okay, so this is the continuous monitoring or peaking problem. And what happens actually is the customer will watch this p-value over time as the data comes in, and they won't have set a sample size in advance, or if they did, they won't bother waiting for it. As soon as they see the p-value drops below their threshold alpha, they say, oh, the experiment is done. I got the statistical significance that I came for. I can stop now and reject H0. And in fact, yeah, so here's a screenshot from the performance summary on Optimized Results page. And you can see metrics which are significant have gone green or red. So it's really tempting for the user to just sit there and wait for a nice green means go. But obviously that's exactly what we don't want them to do. Okay, so why is that bad? Well, the problem is it inflates type 1 error. So if you didn't peak and there were no difference, you only had probability alpha of falsely detecting a difference. But now you have so many opportunities to falsely detect a difference that your type 1 error rate goes up a lot. So this is an example from an AA test where there was no difference. And you can see, if you just watch it over time, there are periods where you falsely reject the null. And in fact, a lot of Optimizely customers said, oh, yeah, we know this. We know it's a bad idea. But surely the effect can't be that bad. Well, actually, the type 1 error inflation can be pretty huge. So here, if you look at the blue line, they think they're getting 10% type 1 errors. As soon as they hit a typical sample size, 10,000 visitors, that's not a lot for a typical Optimizely customer. As soon as they reach that, their type 1 error rate is already 80% almost. And if you took n to infinity, type 1 error rate would be going to 1. Okay, so customers know it's an issue. Why do they do it? Well, the issue is if you could stop early and you don't, there's a big opportunity cost. Because if you've committed to a month and you could have stopped after 2 weeks, you're wasting 2 weeks of using that great treatment. So what they really have to do is they have to think about, they want to be able to balance their power and their sample size dynamically. And it's really hard to do it offline because they have to think about the size of effect they wanted in advance. And now by continuously monitoring, they're trying to do that dynamically. Okay, so our goal here is, at Optimizely, we decided we're going to keep the same interface. So we're going to keep reporting p-values and confidence intervals over time as the data comes in. But then we've got to do two things. First of all, we've got to protect the user against type 1 errors. So we've got to make sure when they continuously monitor, the type 1 error rate doesn't go up. And secondly, we've got to give them the opportunity to trade off power and runtime according to their personal preferences, so they can manage this opportunity cost. Okay, so the first step of that, controlling type 1 error. Well, we define these new p-values, which we call always valid p-values. And these are precisely the p-values which let the users continuously monitor. Okay, so what is an original p-value or fixed horizon p-value? Well, that's saying the probability that the p-value falls below any threshold x should be at most x. In other words, if I look to see if the p-value falls below x and declare significance if it does, that should have type 1 error rate only x under any null hypothesis. So what an always valid p-value does is exactly the same, but we're saying we let you pick the sample size to be a function of the data collected. So that's the stopping time t. So at any stopping time t, the probability that you fall below any x under the null hypothesis should be at most x. Okay, so that's a pretty natural goal. I mean, that's what we want. But like, can you actually make these things? Okay, so to make them, we connect into the sequential hypothesis testing literature. So this is a pretty old field. It's used pretty widely in clinical trials, but it's only more recently getting traction in A/B testing. And the idea is a sequential test is some rule that depends on the data, which tells you when you're allowed to stop your experiment, and when you stop the experiment, should you accept or reject the null. Okay, so you have these stopping times t of alpha, depends on the significance level alpha you're going for, and under the null, the probability that you stop in finite time and reject the null at that time should be at most alpha. And so we require like a few conditions for this to make sense. So if at smaller alpha, that's a small significance level, it should be more conservative. So you should always collect more data at a lower alpha. And you should also make fewer rejections. So if you accept H0 at a high alpha, you should definitely accept H0 at a low alpha. Okay, so how do you get from sequential tests to p-values? Well, at any time during the experiment, you start with a sequential test. Any time during the experiment, you can ask, what is the minimum significance level alpha at which I would have stopped the test already and would have rejected the null hypothesis? That, for any original sequential test, that is an always valid p-value. So that gives us exactly what we need. So what do we do at Optimizely? Well, we use a specific sequential test, which is called the mixture sequential probability ratio test. This was developed some decades ago, and it's developed for the context of a single stream of data. So they weren't thinking about A/B tests. They're thinking about one stream of IID data whose distribution depends on an unknown parameter theta, and you just want to test, is that theta equal to 0? And the way it works is you look at the likelihood ratio between theta equals 0 and some alternative theta, based on the data collected so far. Now, you could do that for any alternative theta, but you put a mixture over the alternative theta. So here I've picked a normal mixture. You could use any mixture. And now you integrate this likelihood ratio against that mixture. And roughly, this is the evidence against the null hypothesis in favor of the alternative hypothesis, and specifically in favor of a mixture of alternative hypotheses that you've specified. Now, if that thing ever gets large, that's evidence against the null. So at that time, you should stop and you should reject the null hypothesis. And if that thing never gets large, you never stop, you always accept the null hypothesis. And in fact, it's calibrated so that under the null, the probability that you ever reject is at most alpha. Okay, so we want to do the same thing at Optimizely. We want to use an MSPRT, but we need to adapt it a little bit for A/B testing, because we now have two streams of data. So we've got a treatment group and a control group. So the only issue then is this probability ratio doesn't make sense, because it's not just a function of theta. It's a function of mu A and mu B. But you can make an approximation, say it's roughly, just treat it as one function of theta. So that's what we go ahead and do. And we construct this new mixture of likelihood ratios against the null. And we reject when that thing is large. So what we get out is this test controls type 1 error exactly for continuous data, for normal metrics. And for binary metrics, the approximation is bad at high alpha, but it's a good approximation at low alpha, and you get approximate control then. So we have a test that gives approximate control for binary and continuous metrics, and we get from that sequential test to a p-value by asking what is the minimum significance level alpha at which we would have rejected. So that's how we compute our always valid p-values. I guess there's sort of one remaining question, which is, okay, we have these always valid p-values which protect the user, but are we now sacrificing a huge amount of power or getting really long experiments. So no. And the reason is, OK, what the user's got to do is they watch this always valid p-value over time. And if it falls below alpha, they stop and they reject the null. So that policy is easy to show, actually exactly implements the sequential test. So by looking at our always valid p-values and rejecting when they fall below alpha, the user's decision policy then is the MSPRT. But our interface does something better than just the MSPRT. It gives the user the opportunity to give up for failure. So if they're seeing the p-value doesn't fall below alpha, then they can give up. So the way we think about that is we say the user has some sample size m at which they would give up. So 1 month, they can't run experiments any longer. They've got to give up, accept the null. And that's different from customer to customer. Some optimized customers can run experiments for a month. Some are very, very pressed for time and can only run it for a few days. So when the user does this, they actually end up implementing a truncated sequential test. So they stop whichever is sooner, T of alpha, i.e. when the MSPRT would stop, or at their M. And they reject the null if the MSPRT kicks in before their M. And this is good because now it handles users with different M's differently. So users with high M's wait a long time. They detect lots of effects. Users with low M have the opportunity to give up, and they get nice short experiments, albeit with lower power. OK, so now the good thing about the MSPRT is it actually gives an optimal trade-off between power and runtime wherever you are on that M spectrum. So specifically, we can think about 3 cases. So we're thinking of of M large, people got a lot of data, and alpha small, you're going for pretty accurate tests. But the question is, how big is M compared with how small alpha is? So case 1, M not big enough compared with log 1 over alpha. In that scenario, OK, the MSPRT has no power, but nothing you could compare it to as any power. So fortunately, not too many customers live in that world because they get no value. Case 2, M is pointlessly large. You can detect, for your significance level, you can detect anything you want. It's possible to get perfect power 1 for any effect with little OM samples. So you can get perfect result, and the MSPRT does get that perfect result. The really interesting case is in the middle, where M is comparable to log 1 of alpha. And in that situation, the MSPRT does give you the shortest experiments for the power it's giving you, in the sense that the MSPRT has, for any true improvement theta, it has some power. You can't replace the MSPRT with the truncated MSPRT with another sequential test with shorter experiments in expectation without sacrificing power at some alternative. So that's an efficient trade-off. OK, so that's the theoretical guarantees for power and runtime. And I just wanted to show you one simulation which confirms what I just said. So we think about a group of experiments which have different improvements, and those improvements are drawn from a normal distribution. Now, we think about this hypothetical optimized customer who has an M which would give them power beta when they use our always valid p-values. We use beta, you can see 0.5, 0.8, 0.9, 0.95. And we compare against the fixed horizon test they would have had to use to get the same power on that distribution of experiments. And this graph shows you the ratio between the two. So our runtime divided by that fixed sample size runtime. And you can see that most of these graphs are to the left of 1. So that means that most of these customers would stop earlier using our p-values. Now, the situation is not great for low beta. So if you're going for really low power, ours are not exactly optimized to give you minimum runtime. But as beta gets closer to 1, then ours do give you the min runtime to achieve that power. OK, that's all the reasons why we thought it was good. And in the beginning of 2015, we deployed it. We went right out and actually deployed it to all users straight away for all experiments. So now, since 2015, all hundreds of thousands of experiments run on Optimizely have been analyzed in this way. I think it's really improved trust in Optimizely. People were pretty freaked out by the old stats. They knew peaking was a problem, and they're pretty happy that now we've solved it, and it's a big differentiator for Optimizely. It's been a really big thing for them. Thank you.